Welcome back to ArtCraft Electronics videos. It's been a while since my last upload, so thank you to all the subscribers who stuck around while I got back into making electronics videos. ArtCraft Electronics is no longer in the manufacturing business, but I'm still regularly building projects that I think may be interesting and useful to viewers. Making videos is now more of a hobby, and I look forward to sharing informative and practical projects with you. My video philosophy follows the miniskirt principle. Long enough to cover the subject, but short enough to stay interesting. I'll explain the components used, the tools required, and how everything connects together. When I mention products, I'll explain why I chose them and where they can be purchased. This video is for entertainment purposes only. If you decide to build this system, you should already be comfortable working with power tools, hand tools, electrical wiring, and most importantly, safe work practices. Can't underscore this too much. Be safe while you're working. The first phase of this project uses low voltage, but no electrical energy is ever completely safe to handle. If you are unsure about your ability to work on mechanical or electrical systems safely, stop here and seek qualified assistance. This is a new phase for ArtCraft Electronics, and I'm excited to share these projects with you. First off, we'll have a simple solar battery charger for 12-volt LiFePO batteries. Let's take a look at the assembly right here. You see it's very simple. Let me get my poker here. We have the charge controller, and we have the photovoltaic disconnect and breaker, and we have the battery disconnect and the breaker, and the battery itself. The connectors are all going to be addressed during this video, or this series of videos actually. And we're even going to put a couple of connectors on the cables. We'll terminate them, just so we know how to do that. Okay, the goal of this video series is to build a simple and cost-effective 12-volt solar battery charging system. Along the way, we'll cover the skills, hardware, tools, and configuration needed to create a basic backup power source for situations like power outages, camping, or any application where 12-volt lights and appliances may be useful. There are many prepackaged solar generator systems on the market. However, they are often less capable, less expandable, significantly more expensive, or some combination of all three. Eventually, this project will either be expanded or replaced with a 48-volt system designed to power critical household loads as part of a larger off-grid emergency power system. For now, this project serves as the training wheels for that future system. The approach here is simple. Present the research, lessons learned, and on-the-job experience involved in building a practical and relatively easy to assemble solar charging system. 12 volts is a very common voltage in automotive and portable applications. If AC powered appliances are needed, an inverter could certainly be added. However, since the project is based around a simple, single 100 amp hour battery, a larger 48 volt system would probably make more sense for heavier AC loads. Again, this project is really intended as a stepping stone toward that larger system. Okay, let's get into the hardware. At first, I considered using an all-in-one controller, solar controller, from companies like SRNE and others. But for simply charging a battery, that seemed like more capability and, bluntly, more complexity than necessary. Instead, I decided to use individual modules for each major function. There are advantages to a modular system. Failures are easier to troubleshoot. Defective modules can be replaced individually. and future upgrades or expansion become much simpler. The charge controller is really the heart of the system, so let's start there. There are many products around that convert solar panel output into the proper charging voltage and current for a LiFePO battery. Some had excellent reviews, but required additional communication hardware for setup and monitoring. Others raised concern about reliability or inconsistent performance. In the end, I chose a Victron charge controller. Yes, Victron products tend to be more expensive than many alternatives, but after researching the options, I concluded the additional cost was justified for this application. The model I selected was the Victron Smart Solar MPPT 120. This controller accepts up to 100 volts from the solar panels and can deliver up to 20 amps of charging current to the battery. As a comparison, I have a furnace backup system that uses a 20 amp charger powered from the utility mains, and it performs very well. It can recharge a heavily discharged battery in roughly 4 to 5 hours. Based on that experience, 20 amps seemed to be a practical and cost-effective charging level, especially considering typical summer sunlight conditions here with a few clouds and the occasional C-130 flyover. The total cost of the controller, including shipping and sales tax, was under $100, so the decision was made. After installation and initial testing, I was very happy with the choice. I purchased mine from Inverters R Us. They had the unit in stock, shipped quickly, and were great to work with. Victron products are also widely available through Amazon and other suppliers. One of the design goals for this project was portability. I didn't want to permanently mount solar panels on the roof. Instead, I wanted something that could be deployed at a campsite or simply set out in a driveway when needed. After doing some research, I found that mounting the subsystem components on a wooden base worked well because it kept everything secure and reduced the chance of loose or intermittent connections. So the initial plan seemed simple. Cut a piece of plywood about 1 foot by 2 feet, maybe 5/8 inches thick. Mount all the components and start wiring the system. Then I did something unusual for me. I read the instructions. The charge controller documentation recommended against mounting the unit directly to flammable surfaces and also stressed the importance of cooling airflow. So, after digging through my box of random useful stuff, I came up with a piece of sheet aluminum and cut it to size, about 6 inches by 5 1/4 inches. That isn't a precise need, but it looks nice on the board and behind the charge controller. 6 by 6 would do fine. Anyway, the aluminum plate serves as a mounting surface for the controller, and it adds at least some resistance to the entire project suddenly bursting into flames during operation. I followed the instructions. Yeah. The plywood and aluminum combination turned out to work well as a mounting platform for both the controller and its support components. This controller itself was mounted using number 8 panhead bolts, nuts, with the bolt heads countersunk into the back of the plywood. All of the hardware came from Lowe's. Well, we've now reached the point where the presentation is becoming longer than the short enough to stay interesting rule allows. So tune in for the next part of this project, where we finally answer the obvious question. I thought this was a solar battery charger project. So where are the solar panels and batteries? Thanks for watching, and please subscribe.